Hello. So this is going to be Waves Lab, Gizmo Lab Activity A video. So the question we're answering is how do we measure and describe waves? To get the Gizmo ready, we're going to do our settings. It's really important in this lab that you pay attention to the settings before you move on to questions. It's a lot harder to figure things out if you have the wrong initial values. So we're going to set our wave to transverse. We're going to set our amplitude to 20. Our frequency is going to be set to 1. Tension will be 2. Density will be 2. All right, observe, click play. Observe the hand and observe the motions of the hand and the green dot in the middle. What is the motion of the hand? Up and down. Turn off the lights in the checkbox and observe the green dot. What is the motion of the green dot? Also up and down. Up and down. Follow the motion of a single crest of the wave. How does the crest move? So if we don't remember what a crest is, we're going to scroll up a little bit because it is defined in the previous section. It says, notice the crest or high points. So that's what we're looking for here, is we're looking at the motion of a high point and how it moves. So it looks like a crest is traveling from left to right here. So how does it move? From left to right. In transverse waves, the motion of the medium, what the wave goes through, in this case the spring, is perpendicular to the direction of the wave. So the wave is moving left to right, but the medium, which is the slinky or the spring, is up and down. So they're perpendicular. They're making a T shape. Left to right and up and down would make a T shape, which would be perpendicular. Next, it says we're going to measure. So with the lights on, so let's turn the lights on. Click pause and turn on the ruler. So we're going to click pause, show ruler. Use the ruler to measure the horizontal distance. So remember, horizon, the sun comes up on the horizon, is across, it's straight across, left to right, not up and down. So we're using the across distance between two crests, which is the high point. And what is this distance? So we take the ruler, and it's kind of hard to get exactly the top, but we're just going to kind of do our best to kind of say right where the center is there. And I'm getting 100 centimeters. So I'm going to put that information here in this box, 100 centimeters. This is the wavelength of a wave. So a wavelength is a distance between two parts of a wave that are the same two parts. Then it says, what is the distance between the two troughs? Now, once again, if we don't remember that term, scroll up. Trough is the low point of the wave. Okay, so we're going to measure from low point to low point. Using the same ruler, I'm going to drag it over till I can kind of hit the middle there, and I'm getting 100 again. So the distance between two troughs is 100 centimeters. Then we get this little important piece of information. The wavelength can be found by measuring the distance between two successive crests or two successive troughs. Successive means the next one, or any two equivalent points. So I could also measure like halfway up this crest and then halfway up the next crest, and I get 100 again. So any two same places on a wave that are consecutive are going to give me the same measurement, and that is what a wavelength is. It's the distance between two same points in a wave that are consecutive. Next, it says to click reset, so we'll do that. We're going to change the density from 2 to 1, and then we're going to click play, and then pause. And then it says what is the wavelength of this wave? So we're going to measure again. I'm going to do crest to crest, and I'm getting about 140 centimeters, which I've already typed in here. This is the new wavelength with the lesser density. Number 3, it says measure, click reset. So we're going to reset. The amplitude of a transverse wave is the maximum distance a point of on the wave is displaced or moved from its resting position. Turn off the lights, click play, and then click pause. Put that up there. Pause. Use the vertical ruler to measure the height of the green trace, showing how far the green dot moved up and down. What is the height of the green trace? Now, the green trace is going to give me the distance from the lowest point to the highest point. It's not going to give me just simply the change. So I'm getting 40 centimeters, give or take. It's not super precise because you're kind of having to guess a little bit. So I'm going to just say 40, even though it's probably not exactly 40. That's going to be an estimate. The wave's amplitude is equal to half its height. So if I measure from the highest to the lowest part, that's double the amplitude. Amplitude is simply the distance from the halfway point to the crest or the halfway point to the trough. So if we were to put the grid on, so the grid, the line here is showing the middle. So when my wave is not moving, it's laying on this line here. And notice I haven't moved the ruler, and it shows that that is 20 centimeters is the middle there. So then when I hit play, the wave moves up and down past that central line. And the amplitude would be read as 20 centimeters. All right. Next page, we're going to switch to longitudinal waves and do some measurements there as well. So let's hit reset here. All right, click reset, turn lights on. Okay, turn off the rulers, select longitudinal waves. Check that the amplitude is 10, frequency is 1, tension is 2, and density is 1. Okay. I'll turn off the grid too for now. Okay. Hit play. Okay. What is the motion of the hand? Left to right and back. And back and forth. Turn off the lights. What is the motion of the green dot? Same. Also left to right and back. So it's back and forth, those two places. Follow the motion of a single compression of the wave. How does the compression move? That is a vocab term. So if we don't know what it is, let's scroll up and look for it. So compression. There we go, highlighted in gray. Compression. A compression is where the springs are close together and the refractions are where the coils are spread apart. So back down to our questions here. The compression is where it's close together. So the compressions are moving from left to right. Measure with the lights on. Click pause. Show rulers. The wavelength of a longitudinal wave is equal to the distance between two successive compressions or rarefactions. What is this distance? So move that out of my way. And then I want to go for where it's the center of the densest part, which is a little tricky to estimate, but we're doing okay, I think, right there and right here. So I'm going to go 140 with that. 140 centimeters. How does the wavelength compare to the transverse wave? See your answer to 2C. to C, 140. It's the same actually. Okay. It should be the same. Next, we're going to click reset. The amplitude of the longitudinal wave is equal to the distance a point on the wave is displaced from its resting position. Turn off the lights. Click play and then click pause. Pause. Use the horizontal ruler to measure the width of the green trace. So remember when we measured the amplitude of the transverse wave, we had to measure it vertically because the medium was moving vertically, not horizontally. In this case, the entire width is 20. Now, if we recall from the previous wave, the total width was was double the amplitude. So the amplitude was only half of that amount. So that means that our amplitude is only 10 centimeters. All right, calculation. Click reset. Select transverse wave. Select lights on. Show grid. Off rulers. Okay. Frequency to 0.5. 0.5. A single cycle is the time it takes the hand to move up, move down, and then back to starting position. Click play and pause after exactly one cycle. Okay. I'm going to try that again. Okay, up, down. Oh, I think we're going to have to reset it. So if you'll notice, it's recording the time right here. And you have to reset it to make it go back to 0 each time. Oops, I've missed the pause button. They're right about this taking a couple of tries. So I'm actually going to take the time it takes to go from the middle up all the way down and then back to the middle. Okay, 2.2 seconds. Let me try it again and see if I get the same number. 2.12. 2.12, but notice that the hand stopped above the line, so I'm a little bit slow. Try that again. Oops. Still too far. All right, so I'm getting 2.12 seconds, but I know that that's a little too far because I'm missing it every time. It's actually going a little bit too far up before I hit stop. But that is the amount of time it takes in seconds per cycle for this wave. So seconds per cycle. Frequency is the inverse of period. So that means that 1 divided by the period is the frequency. So if I were going to do that calculation, I would do 1 divided by 2.12, which it's not writing. 1 divided by 2.12. Okay. And that would be equal to, bring up my calculator here. So 1 divided by 2.12 is 0.47. So 0.47 is the frequency I'm getting. Now, I know that this time right here was a little bit off. I was a little slow, so I know this time is too big actually. And if this number is too big, then that means that this number is too small. Because when I invert it, I'm actually going to get a smaller number if my denominator is bigger. The other thing I need to note here is that I set the frequency to 0.5. And it says I'm solving for frequency here in B. So I really didn't have to do any math because I know what the frequency is. I set the frequency. It's 0.5. And so you can see that with the simulation, I mean, I can only get it so perfect. It's going to be a little bit off. But this is encouraging. This is close. So it should have been 0.5. I got 0.47. That's really good. All right, this is the end of Activity A video.